Good evening and welcome everyone to the 10th working session of 2021. This is the beginning of the end of the year, so to speak, and also it is kind of a continuation or a parallel presentation to the one picking up with the one we did last month that was on analysis and results, interpreting and reporting towards the 2030 metrics. But this last month was focused on architect-oriented tools, particularly front-end comparative tools. And tonight we're joined by a couple of talented engineers who are going to help us architects better understand the modeling process, the outputs of our modeling efforts from the engineering perspective, and help kind of educate us on working collaboratively through the modeling process with engineers. This is, I think, as mentioned, this is the 10th talk this year, picking up on a full slate that we started probably going back to the end of 2019 to try to increase participation in the 2030 commitment through the AIA, and we've been kind of hit the ground running. And once we went to the Zoom world, everything became virtual, but we've been able to get presenters and have guests from all over the country, actually all over the world in some cases. We do have 2 talks coming up to round out the year. Next month we'll be talking about translating architectural models to energy models, finding functional interoperability, and we have an interesting panel already coming together for that one. And then we'll close out the year with a session on designing effective contracts for energy modeling, and trying to write in energy modeling into our projects from the get-go to make sure that we are kind of tracking our projects all along. With that, go to the next slide. So again, why are we here as architects, as engineers? Because the building sector has such a major role in reducing greenhouse gas emissions, CO2 emissions. And so we're obviously focused this evening in our discussion on energy modeling on operational carbon. We've also talked, and obviously we're all talking collectively in the industry about embodied carbon as well in building materials and construction. So we also want to just make sure that we remind everybody of the importance of signing on to the 2030 commitment, and also wanted to quickly dispel or maybe set straight some myths versus facts, about the amount of effort that's involved in the 2030 commitment and in reporting. It is not like signing on to another lead process. It is a process that takes 15, 20, 30 minutes per project, and can be used at the front end of your project too to help you set targets. So it's a very kind of it can potentially be a very useful tool for firms. And so there's a couple of steps to becoming a 2030 signatory firm. The first is to sign on to the commitment letter. The second is to develop a sustainability action plan. There's a number of examples out there, both from the AIA and from other firms that proudly publish theirs on their websites and in their marketing. The next step then is to, once you sign on, is to report your projects, as we were talking about, and that's done through the design data exchange. And we wanted to plug as well that we do offer office hours, and we offer help from our group in terms of supporting people who are trying to learn how to report and kind of develop some best practices on that. And we've had a few talks also focused on some of those subjects. Then once you've reported, as I mentioned, it's also being a part of the 2030 commitment is also a really useful part of pursuing better performance going forward. So once you know how your projects are doing the first time you report, then you can use that to start to develop your goals and see where you're falling short, and use that to inform the projects going forward. And again, one thing to emphasize here is signing on to the 2030 commitment does not require all firms to be meeting the 2030 commitment. This is a goal. We are working towards carbon neutral buildings, but we understand and probably without exception, none of us are there across the board yet. So this is meant to be a positive factor for change and help move us in the right direction. And then, of course, as you do this year after year, you get into your sustainability action plans, review them, see maybe what's working, what's evolving, and see where your next steps are. So as I mentioned, we at part of the AI affiliate code, we do offer a lot of resources, and we are available ourselves. We have typically 2 office hours a month, and you can certainly reach out to us through the AI affiliate code email with any specific questions. But we do record all of these sessions, and just a note to all who are attending, the session is being recorded for reference and for viewing in the future. And we have a YouTube page, AI affiliate code, on YouTube. And again, as I mentioned, the AI actually has recently published an updated guide to creating a sustainability action plan. Also a plug to subscribe to our affiliate code calendar or the AI Philadelphia events for more information. So just a couple of logistical things before I turn it over to Jonky and our presenters. One thing we want everyone should do is use the Google link that's in the chat to register or sign in, if you will, with your AI number to get your CEU credits. Also, as we're going along, please feel free to drop your questions into the chat at any time, and we'll pick them up for the Q&A and for discussion as we go. And again, we are recording, just so everybody is aware of that. So with that, I'm going to turn it over to Jonky to begin our analysis and results, interpreting reporting part 2 session. And I will give you the screen there, Jonky. Let's see if that's switching.
Thank you, Josh. Thanks for that intro, and welcome everyone. We're going to get started. So learning objectives, as Josh already mentioned, so I won't dive into these too much, but the way the session is going to be organized is we have 2 great energy modeling experts. So Sarah is going to be doing full energy modeling, and then Ramya is going to talk about memos and other examples of energy modeling that might not necessarily be a full energy model. And then we're going to kind of, we have some questions, and it's going to be organized as a panel discussion. Where they're going to talk about some questions that we've already vetted, and then we'll open it up to audience questions. But feel free to add any questions in the chat at any time. We'll be monitoring those, and then if they're related, we can bring it in to the session. So I said the names before you saw the pictures, but we have Ramya Sivakumar, who is a certified energy modeler. Is that what that stands for? CEM. And a senior sustainability consultant with Integral Consulting Engineers. And she's joining us from Atlanta, Georgia. And then we have Sarah Gudeman, who's a professional engineer and recently awarded lead fellow. Yay, Sarah. She's joining us from Omaha, Nebraska, and she's the Director of Sustainability at Morrissey Engineering. And with that, let's dive in. I'm going to stop sharing here. Or actually, Josh is going to stop sharing. And
I'm going to start sharing.
Sarah. All right.
Yeah. Once you're done sharing, then I'll share. Okay.
Yep.
And everybody's going to have to bear with me for a minute here because I'm sharing my second screen. I have this like one huge monitor and then there's like the other laptop. So you have to look at some of part of the top of the Chrome toolbar there. So you can check out my bookmarks also. What I mean, we both could talk about energy modeling for this whole time, probably by ourselves and all the different awesome engineering things we could nerd out about for it. But I'm going to try to focus on this kind of concept of the full building or the whole building energy model. And then we'll have time for questions. And I know both of us brought a lot of examples that we could pull from. So when we think about this full whole building energy model, it's kind of the same thing. It's traditionally, as you know, probably what we think about when we think of like LEED or code compliance energy modeling. As it ties back to 2030, ideally, if we're reporting to DDX, we want to do it with this full whole building compliance energy model at the end of design. But as we're going to talk about a little bit more, what we really want to be thinking about doing is the more early on energy modeling at conceptual design and through DD. And I know that was kind of the focus of the last session, the working group 9. So really, when we're thinking about this whole building model, we're really talking about 2 models at least, and a lot of inputs and many, many assumptions. I have a really exciting spreadsheet I can show you on that topic. But really, the quality of those assumptions depends on 2 things. One, the project phase. So how much do we know about the project at that time? And 2, the person making the assumptions, because I know some engineers and some energy modelers that will say, well, give me all the information and I'll run the model. And it's like, well, okay, you can't know all that information at schematic design, and because nobody does. So it's all about having a well-informed team to know what you can assume when and what's a reasonable range of assumptions. And a lot of that honestly comes with time and experience. So I'll use an example here. Plug loads is a great recent example I had on a project. We had a kind of automotive training facility pursuing LEED certification. It was a college building. We assumed something for plug loads at early schematic design, and we carried that number forward. We communicated what we thought that number was. We talked about it over and over, and then by the time we got to construction documents, when we finally did the final LEED compliance modeling, the plug loads were insanely high, and it more than doubled our EUI ultimately on the project. So as we drive down the energy consumption and the increase the efficiency of envelopes and leakage and things like that, this plug load thing is going to be more and more important. So it's really a function of all of the inputs. And I think for a long time on energy modeling, people kind of talked about or were coy about like, what software do you use? Like it was like the secret. If you could just find the right software, then we could all do these energy models so easily. But it's really a process-driven thing, which probably is why I was drawn to it to begin with, because I have that really engineering process brain. But there are some inputs that are more impactful than others. So we're thinking about early on the aspect ratio and the orientation. I think we're going to get to a place where we talk more about like vertical surface to floor area ratios and things like that in future energy codes. Obviously, glazing plays a big part, and air tightness certainly is something we're going to be talking a lot more about as we increase uptake of like enclosure commissioning and newer, more stringent energy codes. Certainly with rating systems like Passive House as well. So other things, more inputs, plenty of inputs here. Occupant density is a huge one. So I know it's sometimes hard to have those conversations and get that information early on from the owner of like, how are we going to use this space or this specific area? Is it a once a year event that we need to maximize the peak loads for the HVAC equipment, or is it one time that might happen during a swing season? And like having those conversations in a really organized and structured way is critical early on. So not just the occupant density, but also the schedules is really important. So who, what, where, when, and how for thermostat set points, lighting schedules, people in the building, and then the all-important plug loads as well. So really this, this whole building or full building energy model, we think of it as this is kind of internally the steps that we've laid out, these 1 through 9, and they're based on ASHRAE standard 209. But really, historically, this energy modeling piece has been this, number 7, like at the construction documents phase of the project. But what we want to do is these earlier models, we can explore more options, but we can't like optimize everything all at once. So it's kind of like we want to move down the options, narrow down the things. And sometimes on projects, there's things that cannot be changed. Like there are absolutes in terms of orientation or, shading or structure or other things that are on the site. So we just need to know what those are earlier on, have that conversation and move down to something which is going to look like this in terms of a deliverable. And you've probably seen some of these types of graphs, certainly if you've worked on a LEED project, this energy end use concept. So when we're thinking about even early modeling, ultimately it comes down to these buckets of energy that are being consumed within the building. So we need to know how much energy, and there's some good Sankey diagrams later that I know that you're going to get to see. But how much energy is going to heating, how much is going to cooling, what's water heating, interior lighting, exterior lighting, miscellaneous, unregulated loads, essentially all those categories from the energy code that are being regulated. And I know that these are not the most exciting thing to look at, but it's better than something like this, which is what you get out of eQuest, for example. And it's a whole bunch of numbers that then somebody has to generally take and put into something exciting like Excel or Tableau or Power BI or some other kind of data analytics, and then present it in whatever way. So the data, it's important that we get quality data out of these models, because then that's based on the quality of the assumptions that we put into them at whatever phase. But then also the translation of that information into kind of digestible chunks is really important. And I have an example report that I'll show too. But before I do that, as a reminder, energy modeling, like so many things, holds true to these kinds of services. You can have good, cheap, or fast, but you can only pick 2. So I know you've heard other presenters probably talk about this, where it's like, give me an energy model. Like something that people say or hear a lot is like, I need one of those energy models. It's like, okay, well, when do we need it? How accurate does it need to be? And how good is it in terms of fee and cost? Because all this is ultimately time. Like if you have, depending on what kind of scope and project, you can get bogged down in like endless iterations of things. But if you have a quality modeler on board, they could help you, steer you in the right directions between what's going to be valuable to spend that time and look at. So all that said, I'm going to stop sharing this and I will start sharing this, which is an example. We're getting there. Example of a whole building, full building energy modeling report. This was a final LEED documentation report for a project that we completed recently. And I think, again, these could be like endlessly long and they're not super great to read. But you have to want to read them. But, we try to, or, should be emphasizing, whoever you're getting these reports from should be emphasizing the information that you want to know kind of up front here. So there's a summary, you're going to get 29% cost reduction, 12 LEED points. And then again, I think it's helpful to kind of chunk this out into those categories. So occupancy, occupant diversity, and regulated loads like the envelope, the heating, ventilation, air conditioning, domestic hot water, and then just summarizing like this is also going to go to the GDCI review team too. So kind of cueing like these are the reasons that we are saving energy in these charts that you'll see later on. Plug and process load assumptions, humidification. This was a museum, so that was kind of a big deal. And then the inputs, the input summary is a lot of information. But this is something that I think is critical to track throughout the design process. So each deliverable that hopefully you're getting is coming with these input assumptions. So then somebody's theoretically taking them back to the owner and going through them ideally in a meeting with the modeler or with an engineer or whoever, and checking like, oh, is this the right ventilation rate? Are these the right lighting power densities? And this stuff, you know, like I said, changes throughout design. So sometimes there can be pages and pages of those inputs. I have a spreadsheet with multiple tabs that I sometimes ask people to help me review, and they love that. But then here's those charts again. So we're talking about proposed versus baseline. Those energy end uses are important. Color coding is always nice. And here's the kind of summary charts in that typical lead format. We're looking at proposed versus baseline. So there's just different columns. I think, you know, again, separating these out by energy end uses and making sure everything matches up is always really important. Reiterating those results here, talking about any kind of big, like, why are these numbers so big on savings for humidification, or like the bigger numbers should have some explanation behind them. And, you know, generally anything that you look through this column here with this energy savings column should have some explanation somewhere else in the report. So this is only 6 pages, like not too bad, I think, in terms of what could be, because when we get these reports out of the softwares, depending on what software is used, they can be pages and pages. And a report like this, you know, could be generated with any energy modeling software. Like I know I showed an example of eQuest before, but I think this one we did in IES. So that is all I have for now. I'll turn it over, stop sharing, and yeah, we'll talk more later.
Okay, so can you see my screen now? Okay. So I like this quote because too often energy models can tell completely different stories based on how we calculate or interpret the results. So for today's session, the goal is to demystify some of the outputs and reports. And hopefully you all will get to see a pattern or a method to this madness. So what you see here is an output straight out of IES. This is a very basic report. It gives you some information. So very quickly, I'm able to see that the EUI of the baseline is 39 kBTU per square foot. The proposed is 25. It gives you a donut chart that is able to you know, draw out the proportions of the different end users. What draws my attention is that the project is showing, very high savings for fans and interior lighting. As you can see here, 4.4, 2.9, 13.7, 7. So when I see this right away, I'm thinking, well, they must have really efficient lighting, or, you know, some of the inputs are incorrect, or that, you know, how are the fans operating? These are things that are going on in my head as soon as I'm looking at these reports. I'm looking at the bar chart here, and I see that the blue is less, which is supposedly cooling, and then there's a lot of black, which could be, I'm sorry for the images, for some reason the Google slides didn't translate into high resolution images. So it's the fans or the receptacles are not looking exactly how I'd want them to look. But then I also realized that the limits are different. So this one goes from 0 to 80. This one goes from 0 to 120. So I just keep all that in mind when I'm reviewing reports. I also scroll down and I see here the PQs, and I see that, again, the limits are different, but I see that the baseline peak is higher than the proposed. So that gives me hope that there is something right going on in this energy model. The first thing that anyone would do as soon as they want to understand the energy usage of a building is to benchmark the building. There is a zero tool, which is very easy to use, very friendly. So very quickly, you are able to see the, you know, from 71 to 15, that's the sort of range. It's a big range, but what that tells you is that 15 is really aggressive. And so 60 is about, what the CBEX data is saying that an average office, the energy consumption or the EY should be, which is the kBTU per square foot per year. And then the energy modeler would have provided you with a 90.1 or a baseline, and that should be around 39, and this is around 50. So very quickly I can see that, around 20, 25. So very quickly I can see that there are some energy conservation measures that have been applied here, and we want to validate that as we move ahead in our analysis. So here, as we saw earlier, the fans and what is this? And lighting, we see a lot of reduction in these two end users. And then when we look at this, tabular column, what we do see is that the space heating and cooling don't show any savings, but then there's a lot of savings in lighting and fans that we already noted earlier. But what I'm also seeing is that there's a huge amount of savings for fans. So I want to know what kind of controls have been implemented in the model so as to achieve this amount of savings. So is this a constant volume system versus a variable volume system? So those are the kind of questions or I would have for the energy modeler, or as an architect, you would want to justify or you would want to just go through that with the energy modeler. Again, this is a building based in Atlanta. It's 20,000 square feet. So what if this was reversed? What if heating was, it shows here that heating is higher than cooling, for example. So this is something that I would definitely check as to why heating is higher than cooling in Atlanta. So that there are some basic checks that you would do just based on the climate zone that you're modeling. So these are a couple of observations that I would recommend anybody receiving a report go through. If you aren't familiar with the climate zone, then going into benchmarking and looking at CBEX data, looking at other projects in your area would give you a good understanding of what the end use, percentage end use should be like. So once I've figured that out, I want to zoom in a little bit and I want to look at the building peak load components. So as in what are the end users that, and what are the end users or heat gains or losses in the building that provide the, that add up to the peak load in that particular building. So immediately the first thing that I see is that the cooling load occurs on July 15th, which is okay. But what if this occurred in a swing month? So I want to ensure that my inputs and my assumptions are right so that the peak load occurs at a time that I think would be appropriate for that building, space type, and that climate zone. And likewise for the heating load. Here, what I can see right away with the different, like you see wall, roof, conduction, you see window, glass conduction, solar, glass solar, you see occupants, lights, equipment, the different end users that contribute to your peak cooling load. And very quickly, I can see that the occupant and the lighting are really huge here. So my very first instinct at this point would be how are the occupants modeled? How many have they modeled? And is that realistic? For example, if I'm assuming if this were a dining facility and I'm assuming all the 2,000 people are in this particular space at this particular time, is that justified? Are all the 2,000 occupants going to be in that space at that particular time? So just understanding that and reflecting on whether the inputs make sense is very important part of analysis. And likewise, you want to look at the demand, right? The total demand for cooling, interior lighting, receptacles, for example. These are very simple calculations because they are input as watts per square foot times your, the number of hours it gets utilized and the diversity that's applied to it. So these are very straightforward calculations. They do get complicated when you have sophisticated lighting controls, but generally it is a good gut check to look at this and say, does this make sense? As an energy modeler, the other thing to also look at is what is the CFM per square foot. Sometimes you have rogue inputs that could result in really unrealistic CFM per square foot or CFM per ton. So those are the kind of inputs that typically an energy modeler or somebody who is looking at an engineer would be looking at these inputs. But these are also some things that very easily an architect can request and also look at to understand the building and how it operates a little more. So this is a trace, a typical system. It's called system checksums in a trace report. And as you can see, there is the cooling peak and there's the heating peak. All these are envelope related loads. These are internal loads. And you can see that the internal loads are all zero in the heating peak. And that's because you don't want to assume that the lights are on when you are sizing for that peak time. Here, right away, what I would draw your attention to is what is the total here. So the total of the envelope is 485,485, whereas this one is 917,174. So what this tells me is this is an internally load driven, the system is serving a space that is internally load driven. So these are some important items to look at. I would also be looking at the total area to see whether it is justified that this is the area. Sometimes the areas are off. It shows whether there is roof, there is wall model. So these are important checks that any energy modeler would do. And these are some sort of really common sense checks along with the CFM per square foot and CFM per ton. Once we've done that analysis, we are able to then take out all these numbers from an Excel format or through an Excel format, and then present this in the Sankey diagram where we are able to visualize the different end use. Now, let me just say that these are different projects, and I've just grabbed them from different projects and stitched them together. So therefore, this EUI of 36 may not be related to the EUI of 39 or 25. So very quickly, we are able to see, okay, what is the percentage of the end use that makes up this total EUI? And then what is the contribution of the cooling and the heating system? At the same time, what is the impact of solar, lighting, equipment, or ventilation? So if, say, the architect wants to really investigate what is the impact of wall on this particular project, that is only amounting to 3% of the entire, entire load component. So solar is actually 36%. So reducing the solar heat gain coefficient would actually yield better results than actually looking at the wall assembly. So there are just a lot of things that you can learn from this particular characterization graph. Also, you can learn these free heating, that is through passive solar gains, occupant gains, lighting gains, or through losses, conduction gains, conduction losses that can help with the cooling of this particular project. And then what you can drill further down. You can go level 1, and this is level 2. You can look at how that same graph that we saw, the same report that we saw out of trace, can be visualized to show, for example, this is level 2, therefore there is some cooling load associated with the roof, whereas on level 1, we don't see that impact. So this is just a way of visualizing the trace report just to see which one, like for example, lighting seems to have a lot of impact here on the load here. This one is a senior living facility in California. So lighting seems to have a lot more impact on this particular project. And therefore, based on this, we can then go through a lot of these sensitivity analysis where it can say which gives you the maximum bang for the buck and where is that tipping point or the optimum point for, say, glass U value or SHGC or LPD or EPD. And similarly, same analysis can be done for, say, shading. For example, you use the same, for example, the trace report, and you can use overhangs, and it spits out the same information, whether it's trace, IES, or whether it's eQuest. They all have the ability to provide these results. And really, when you model like a shading, it can show you the potential for reduction. So it's all in the number format that needs to be converted into a visualization way, whether it's through like Tableau or whether it's Excel or any other way that you'd like to visualize. Same thing can be done for the window to wall ratio, and then this is put together in this sort of a rendering to visualize it and to for immediate impact, rather than just produce like sheets and sheets of tabular column that basically provide the same information. Again, and then you take that forward and then you try out the different HVAC system options or retrofit options. So this is the same residential, senior residential facility where we tried out different options. And so while reviewing these results, I'm looking for, okay, so option A1 had a roof change and a storm window change. A2 has only a roof panel change. So when I'm looking at the results here, I want to see that difference. I want to see that A1 is better than A2. If this chart were flipped or if the bar was flipped, then I know that something's wrong. So I know it's not always as simple as this, but this is sort of the beginning of just testing out, okay, what are your assumptions? What is your hypothesis? Are you thinking that A1 is going to be less than A2? And then if it is, or if it is not, then you investigate why it is not. And that could be going through like detailed hourly reports or, just generally checking the inputs once again. Similarly, putting together all those different systems, like in this format where you look at all your net heat gains, annual heat gains, and all your heat losses. Again, all that information comes from those reports that I showed earlier. You export them into Excel, and then you bring in all this data and you tally them, and then you compile them in this format. And very quickly, you can see here that roofs have a huge impact, lighting has a huge impact, windows has a big impact. So that's that gives me information to go ahead with whatever retrofits have been suggested. So this is, then we produce this sort of an EUI graph that look at the different options, and then you identify the option with the lowest EUI. In this case, it was the one where you change the roof, the window, and then some other retrofit decisions, which is option B. So I want to, end this session by asking this question, like, what do you infer from this graph? I think recently on this one project, we ran several parametric analysis, and then this was the graph that we could plot out of this. And, suddenly we were a little stumped when we looked at this plot, and we realized that, interpreting data is often about asking the correct question. So you could very well look at this graph and say, oh, so it's okay to actually not really have a tight building because it seems like, it doesn't have, like, what is the heating kBTU per square foot per year compared to the cooling? Like, what is this impact? So it's very easy to look at that and say that, okay, if you don't have a tight building, then, it's one way or the other. Or if you have a, infiltration, it actually helps with cooling or doesn't help with cooling. So I think it's important to look at this and say, what is the right question to ask? So if it does help with cooling, as is shown in this particular graph, then are there opportunities for natural ventilation or an economizer? So those are the kind of questions that we should be asking and discussing together. So that's it.
Thank you, Ramya and Sarah. That was really informative and really great. And I'm sure we want to unpack some of the stuff that you just showed. So I'm going to share my screen here. Just give me a second. Oh, sharing the wrong screen. There you go. And we're going to pick up where you left off with our questions. So I'm actually going to skip this first question and then come back to it at the end. And I'm going to, switching up the order on you for a bit. So I wanted to start with so what can you tell us about what are the most important inputs, right? So we talked about the different inputs for whole building energy modeling and how that impacts outputs, but what are the most important inputs for an energy model, and how can architects and engineers work together to validate those input assumptions?
I'll jump in because I'm excited to talk about inputs. Obviously, I really think the most important thing is the thing that's hardest to kind of put your finger on, which is how are the occupants actually going to use the building. It's not just how many people, and beyond that, like how many of what type of people, like what are they doing in the building? Are they just sitting there calmly? Are they running around? Are they children? Are they adults? What age and demographics are you having in the space? And even within the building, space to space, that's going to vary. But beyond just that, which is a lot in and of itself, there's the schedules, there's the set points, and then there's the what if somebody does X, which we don't really know until they move into the building, and then you get into the whole topic of measurement and verification. But people, occupants, occupancy, how the building's operated, it's that topic.
Yeah, what I'd like to add there is that also what is the purpose of the energy model? So for example, if it's a comparative study, then it's not absolute values that are important. It's more about testing of what are you looking to get out of this energy model? Is that just you want to head in the right direction? Do you want an absolute number? So I think that will depend on what inputs are there in the energy model, because ultimately most energy models are wrong. Some give you the right answer or the correct answer.
That's super important. I think you mentioned earlier, right? Asking the right questions. And that's totally one of them. What are we trying to find out by running this model? Is it the EUI? Because it's not always. It's those comparative, what is better than what else, kind of leading towards a goal.
Awesome. So thank you, ladies. We did get a question in the chat box, which is kind of tied to our next question. So how do those, I guess it actually isn't, there it is. How do inputs vary from tool to tool? But the question we got in the chat box was, how does program types affect the question or inputs that are needed? So kind of if you can do the two together, what other factors might influence?
I can go first. So like Sarah mentioned, it really depends on how fast we want the answer. And sorry, what was that question again? How does program affect the questions?
Yeah.
Okay. Yeah, so it really depends on how fast we want the answer, how sensitive it is. Is it for PV sizing, for example? Is it for making retrofit decisions, or is it a design tool? So I think it would vary time to time. Personally, if it's a quick and dirty model, I choose eQuest, for example, not saying that that's the best or not. If there is a little bit more time, then it's IES or Design Builder or Energy Plus. If it's very nuanced, it needs very high-end questions and answers, then it's probably Energy Plus. So I think it really depends, and each of these inputs, each of these tools have different ways to input the information, but it's still the same information. It's still the information that Sarah showed on her slide, which is occupants, lighting, all the basic inputs, the schedules, it's all there. It's just different ways of putting the same information in different tools. I don't know if I answered that question.
No, that was great. It
was good. Yeah.
It was great.
I'm fond of saying, I think the best tool is generally the one that the person using it is the most familiar with. Because if you're not familiar, and that's why I think some people will, defer to eQuest, or like I did a lot of modeling in like Train Trace 700, like again, like that's kind of a clunky software, but if you know how to get results out quickly and how to interpret them, more importantly, then that's really important too. So I think we've kind of, I don't know, most firms that do energy modeling seem to use a variety of tools depending on what the question we're trying to answer is. And also for us, what our clients are using. If we're doing kind of this collaborative back and forth modeling, like, are you doing energy modeling? What software are you using? Or are you just, what kind of graphical software are you doing your early design iterations in? Is it SketchUp? Is it Rhino? Is it Revit? So that kind of feeds into it too.
Yeah, it depends on the question too. Like, for example, should we have a second wheel versus, should we have, what kind of glazing should we have, or what kind of shading we have? So different softwares have different capabilities. So that affects it.
And I know this isn't about daylighting, but like, how does it integrate with the daylight model too? Like that's something that we talk about in our office, because we use different software for different things. And I think when it gets to 2030 reporting and the DDX too, like if we're just trying to report a number, just trying to get to an EUI, then that plays into it too, in terms of when do you do the modeling if there's not, some kind of integrated modeling process in the design planned. Since we're a 2030 signatory firm also, it's like, well, we're going to do the model, but nobody really wants to know nobody's asking the questions that we can answer early on. So we just want to do the model as quickly as we can when we have the most information, which then is like later in design. So.
Well, that's really interesting perspective. That I feel like we can make a whole session out of, engineering firms that are 2030 signatories and all of the work they're doing that architect or like, your consultants or your clients might not even know about. And that's a really great segue to a question that Paul's asking in the chat box related to this topic. Like, have you found that owners and users, like what inputs have you found owners and users find important? Let me rephrase that. What inputs are important according to owners or users from your experience for the results? Is there a way to distinguish what owners are looking for versus, I guess, designers?
So I think there is a huge range right now. I think in the Southeast, for example, a lot of it cannot be cost driven because the electricity is cheaper than elsewhere. And so the focus is a lot more on, say, comfort, health, wellness from that perspective. So the inputs that are important to inputs or results that are important for the owners are very comfort and health and wellness driven. But I'm pretty sure that, in the Northeast or in California or other states, first cost can also be a very attractive, outcome or a result out of the energy model.
Yeah, and I think that gets into another question that's in the chat about modeling first costs and payback periods. Because I think what a lot of people are interested in is the cost output. And I think something that we talk about a lot is how even these whole building models that we're completing with the best possible information that we have at the end of construction documents are not necessarily predictive models that are going to give you your utility cost budget for the building, right? There's requirements when we do these, proposed and baseline models for LEED or for code compliance or whatever, or even like, tax credits and things like that. Like there's rules and how you have to make those models, and they're not always indicative of what the utility spending will be, which is something that we get asked quite frequently, like, well, what should I budget for utilities for this new project? Like, that's a thing that people are interested in. And then certainly the first cost. So we try to tie those things together too. I think a lot of people are working on that also. So saying, yes, you might save, a $250,000 or $500,000 to put in electric reheat on the rooftop units now, but in the future that's going to cost X number of dollars, with utility, and then you have to explain like demand charges and not just energy consumption, and it gets a little complicated. But yeah, I think that's really important. And then temperature set points, because that's primarily still how we control our buildings, is based on thermostatic set point at whatever zone. And as we're getting more into indoor air quality, which again could be its own separate topic, but controlling buildings to meet temperature set points is what we do mostly still now. So we need to understand what are the reasonable ranges for those set points to be during, both for design and peak equipment sizing, but also for ongoing energy consumption and how people are going to be comfortable or happy with their thermal environment.
Yeah, and what I do want to add is that what is very clear though is that the whole owner request is moving towards a data-driven approach. So they don't want us to just say this is it or this is what we think is best. They want us to show through data, through numbers, through information that we present, that we are arriving at the answer or heading towards the right direction based on our analysis. So I think that is really important, or the most important thing that I'm also seeing with the owners.
It's funny, I'm like just vigorously nodding like yes, but because I think there's a lot of times where it's funny, you could just say, somebody will ask a question like, oh, would X save so much energy, or would this really impact our EUI? And like from your experience in whatever climate zone and project type, you could just say like, probably not, but like that's not an answer people want to see. It's like, show me the data, show me the numbers, and I appreciate that.
I'm going to switch to, there's a bunch of questions coming in, but I wanted to just quickly touch upon outputs varying from tool to tool. Is there anything you can talk about how that might impact your process when you're like, if a client is mandating that you use a tool or you have to switch tools for a project?
I can take that first. What I've seen through the years is that whatever tool we use, we, at least where we are right now, we have to do post-processing anyway. So the outputs, the kind of information the outputs present are very typical. They are just presented in a different format. Whatever format it spits out, taking that information and massaging it and providing it in a easily digestible manner. I think that's the strength of a good building performance specialist or a firm that is actually doing that, so that it's an easy read. Too often things range from they're so beautiful to look at but I can't understand what it means to this could have been presented slightly better, it just looks really sad. So I think that's the range. And so if you can hit that right note, whatever inputs you get out of the tool, unfortunately, I don't think we're at a place where we have one tool that does everything and does it amazingly. I think that's where we are.
Awesome. Sorry.
I'm just trying to read Brian's question in the chat.
There are a lot of questions there.
I'm excited. These are great questions. I want to go back to the one on any concerns. Paul asked any concerns about liability for not predicting energy use accurately. because I think it's so interesting. It gets into, well, it gets into the next question too, but it's almost like thinking about the world of ESCOs, right? Where somebody comes in and says, hey, I'm going to save you X number of dollars of energy, and then you just pay me a percentage of the savings. But I'm also going to show you what you would have spent had you not done this project. And it's all this like, if these 100 things happened, then it would have been this. But if these other things happened, it's that. So I mean, thinking about, I've never had somebody come back and say, hey, you said it was the utilities were going to be this and it wasn't that, because I think there's a general understanding that what we're trying to give in terms of information is slightly more informed than just like a square footage basis for utility budget, which is what I think a lot of people end up doing. But there certainly is a liability if there's some kind of like net zero requirement in the RFP or integrated, design delivery process or something like that. So it depends, which is my favorite answer for everything. It depends on contracts really, and what was set up, I think, initially. And then the post occupancy and ongoing relationships of like building function. Yeah, for sure. Because that gets into ongoing commissioning, monitoring based commissioning, and then measurement and verification, which I kind of touched on briefly. And I think it does tie back to the energy model. So having somebody that can, if they're not involved in a post occupancy capacity, to be able to give a report or give information in a way that's easily decipherable, that somebody then can go back and look and say, thinking about back to the Sankey diagram, right? Like electricity is this or gas is this, and how does that compare to my bills? And just like, what does that information mean? So
regarding David's question, what I would say is this has been one big thorn in my shoe, or whatever you want to call it. And it basically comes from the fact that there's no budget for this unless the owner is actively seeking for this kind of analysis or this information. And so a lot of times in my previous firms, or in my current firm, the energy modeler or building performance specialist or the firm itself does it out of its own initiative, and more like a marketing budget, and sort of like a learning tool for its employees. But yeah, I think there needs to be more robust process and fee allocated for this, so that this does happen. I think we can get there if we try to start sneaking in language for that in our proposals, but that has to happen.
I think at a minimum, what seems to work reasonably well is to kind of offer some free education, again, like from a marketing budget or something like that, to say, hey, there's this free tool called Energy Star Portfolio Manager. Have you heard of it? Why don't you put your utility bills in here, or designate a person to do that, and then share it with me. And then, we can kind of do that back check sometimes. But yeah, it is more rare than we would prefer it to be, probably.
And I think the other thing is to build a sort of, from an MEP perspective, to build a sort of good relationship with the building facility staff, so that they do want to give you a call when they're just deciding to change things, or, so more often than not, you set the building up right, the commissioning, everything is done right, and then the design team leaves, and then the facility staff comes in and just does their own thing. So I think having that relationship, or establishing that relationship during the design process with the facility staff, is also a good way to ensure that building continues to operate as it's designed, and which means that the facility staff needs to be in those design meetings or those design decision meetings, so they feel like they have a skin in the game.
Awesome. And just for the recording, I wanted to just mention that David's question was related to post-occupancy and relationships with owners, and how the building actually performs. Just anyone else who's not able to read the chat box. So those are great answers. And so I'll leave it, we either have time to go through the rest of our questions, or we can just switch to audience questions, especially since there's about 5 questions that just came in from Brian. I'm thinking we skip our, there's one more question that I would do from our preset list, and then we'll switch to the very specific questions that we have from Brian. So I guess we touched upon this a little bit throughout the talk and throughout the presentations, but like, is there some kind of process that you use internally to QA/QC an energy model before sharing it with architects?
I'll start on that real quickly. Yeah. I mean, first, depending on the project phase, but generally like looking at the EUI first is the first thing I'd look at. Like, does this seem at least somewhat reasonable based on the building type and the 2030 target and the, CBEX baseline? And from there, then looking at the energy end uses, the heating, the cooling, the lighting, the plug loads, like based on the climate zone and the building type, and then looking as a percentage basis, like from, what percent are these things of the whole building energy use intensity? Like if the lighting is showing up at, 60%, like, well, that might be a red flag, depending on where it is. And then looking at the baseline compared to the proposed. So checking percentage savings between one and the other along those categories. And then, so it's kind of like from the final end result back to the beginning, then back to the inputs and checking, do these inputs seem reasonable? Do they reflect our design? Are they changing throughout design? Like another red flag would be if we had some input at schematic design and then it stayed the same all the way through to construction documents. Like that would be another red flag for me. Like, did somebody never go back and check this again with somebody? So.
Yeah, I think I would say that having scheduling time, a lot of times what I've seen is that it's just the intensity and the speed at which results are required. There isn't a lot of time for QA/QC, and so I think there needs to be sort of continuous education within the team that is actually doing the energy modeling, so they have opportunity to discuss strategies or processes for energy for modeling different design ECMs as an overall. And then for lead models, there is a very stringent QA/QC process just because it's going for lead, we're going to get review comments. But it is those memos and those individual sort of investigations that sometimes don't go through a QA/QC process, which is why it would be nice if like the architect can actually sit down with the building performance specialist or even the mechanical or MEP engineer, sit down and just go through that and say, hey, is this in the model? Is this in the model? Have you done this? Have you done that? So I think having a discussion on that also will really help.
Awesome. All right, so let's do Q&A. There are some really very specific questions and they are organized by topic. So let's start with window to wall ratio. So it's not directly related, but how do energy models take into account plenums? If they're not used for return air, the thought is that it wouldn't impact energy significantly. So should they be weighed differently, or is there like a factor that gets applied, especially when you're doing a window to wall ratio, as that area not being part of the wall? If it's not conditioned and it's just kind of like an opaque wall beside windows. What would you say about that?
So energy models do take into account plenums for window to wall ratio. So you wouldn't be able to get the window to wall ratio right if you weren't modeling plenums. So that's another good check to see if your window to wall ratio is too 80, 90%, something's off. Plenums haven't been modeled. It depends on the systems and how different tools, different softwares have different ways it accounts for that plenum heat. And so it just depends on the type of system you're modeling, whether it's an underfloor air system, or what kind of system has been modeled. But I would say that plenums are modeled, but then the impact of that plenum on your results would depend on, say, the size of the building and how, like, is it a small, 10,000 square feet building versus like a 1 million square feet building. So I think that impact would differ. So if you want to really study the impact of a plenum, you would, zoom in and study that in detail. If that is a cause of concern, that is.
I thought of a couple of things too in that question, like the window to wall ratio calculation also depends on what energy code you're referencing. If it's 90.1 versus IECC, if they look at above grade wall area differently than gross wall area. And then the topic of spandrel always seems to come up, like, is that window or is that wall? And I generally tell people, like, if it's insulated and performing to the opaque wall value, then you can count it as opaque wall and not necessarily window. But it depends on the construction of the spandrel. Like if the heat is getting into the building, and this is getting into like kind of the building physics side of things, but it doesn't really affect, it affects the energy consumption of the building differently. But that is taken into account in the model. So the heat gets into the building one way or another. And this, blinds is another topic where we kind of talk about this, like interior blinds versus exterior shading. Like if the sun is hitting the building in the cooling season, it's going to get in and be absorbed somewhere, and then it has to be mitigated. And then depending on the system type, it does have an effect if it's plenum return or ducted return or DOAS, underfloor or whatever. So all of those things are taken into account, or should be taken into account, but sometimes aren't, depending on different softwares and the specificity of the modeling.
Awesome. So Sarah, you mentioned spandrels and curtain walls. So one of Brian's questions is, New York City is now saying that insulated curtain wall spandrels are not the same as, or not as true opaque walls in their codes, right? So because the spandrels have more thermal bridging, and how does this affect your earlier models?
I didn't even see that question yet. But
yeah,
I don't necessarily think it is wrong to interpret that spandrel is not the same as a true opaque wall. Certainly thinking about continuous insulation and the feasibility of that on a spandrel wall compared to an opaque wall. I don't know, though, in terms of window to wall ratio, like that's kind of the question that's still open for interpretation, I think. Like if you're over, and that really only matters if you're going, kind of a prescriptive compliance path. So maybe it's a moot point, but I'm not sure if I'm answering that question though. How big of an effect does this have on early models?
So I just wanted to add something about thermal bridging. I would say that a lot of the current tools don't have the capability of really modeling thermal bridges, automatically. So I think that would be something that might have to be modeled externally using a different software, maybe Therm or Ufi or some other software, and then using those results and incorporating that into the energy models. Again, it's sort of it's an assortment of different tools that you have to work with to get the kind of answer that you want. So like you can have a macro answer, and then you want to zoom in and really see the impact of a particular wall assembly. Then I think we end up using more, sophisticated tools. So, and then those answers don't sort of directly translate into EUI. You look at that as a standalone, question, standalone answer. That heads you in the right direction, but not necessarily like, oh, does it give me like $500 saving per year? Does it give me $1,000 saving per year? It doesn't translate like that.
Yeah, and the thermal bridging thing is interesting too, because I think that's another topic. Thermal bridging and air leakage, I think, in energy modeling have been kind of largely like Well, it's probably maybe about this kind of thing, and you apply some factor or assume it's something, but I don't feel as an industry have super great data on those two things yet, and what they should be, because I think thermal bridging is certainly something that's definitely under accounted for in current modeling software.
Awesome. Because I think what Brian, you can correct me if I'm wrong, because I think you're still on. I think he was just trying to guide architects away from, like, what could be done to guide architects or designers away from an all glass building from the get-go.
Right. Okay. Or something that appears, which you're going to save money by getting rid of all that curtain wall too.
Yeah,
So.
right. Talk about first cost savings.
Awesome. So just circling back to the window to wall ratio, what about roof parapets? Do you include that in your energy model as part of your window to wall ratio? And like finding the balance, it seems a passive house requires you to insulate them on all sides.
Yeah. I just finished all my passive house consultant training stuff. So that was the first thing I thought of. I'm like, well, it depends on how the insulation is. But I think it also depends on your code enforcement, right? Like if they're going to look at that and say, you know, I'm looking at the elevation, that's window to wall. I don't think it counts, but only if you can kind of justify it with the physics.
Yep.
Yeah.
Janki, my question was more, should you exclude it from the window to wall ratio?
Yeah.
And the passive house question was more like, just on any building, treat it like a passive house and wrap it over, you know, and tie it into the roof insulation, which can be tricky at a coping.
Yeah.
So for the window to wall ratio, I typically don't include the parapet in my calculation, just because that parapet is not next to a conditioned space. But if it were a small building, and if there is scope and there is time to really assess it, then I would do a therm calculation to really look at that impact of that insulation there and come up with you know, the U value, approximate U value for the wall itself. So that way I would definitely include that, but not in terms of window to wall ratio.
I want to talk, I love the comment on floor to floor heights too. Can we talk about that one also?
Yeah, definitely. Reducing floor heights. Go ahead, Sarah, if you want to take it away, and its impact on fan energy.
Yeah, so floor to floor heights and fan energy effects. And I think I just want to talk about fan energy effects because I'm also a mechanical engineer. So I think it's something that it's kind of an afterthought. Like after we get all of the, you know, the programming and the spaces and the form and everything's laid out, and then we want to, you know, we think about ceiling heights and floor to floor heights, and then it's like, okay, then put some ductwork in here somewhere maybe. And we end up with like the weird transitions around structure and coordination issues. And like that, when I see things like that, it just, like the alarm bells go off in my head of like energy. And that's like forever for the whole life of that ductwork, which, like, I know it's not oftentimes counted as a permanent part of the building, but I mean, I don't know a lot of projects that have replaced their ductwork ever. So it's going to be there for 20 years impacting the energy. It's just like making a decision to, you know, use less insulation or not using a thermally broken window frame. It's like that duct transition is going to increase static pressure forever of that system. And at a worst case, use more energy, or at a best case, use more energy. At a worst case, inhibit airflow to the point that it's not going to perform the way it should. So even in instances where we don't have flexible ductwork, which is a whole separate issue in residential. So it could be modeled. Yeah, go ahead.
Yeah, I was just going to agree that, yeah, it can be modeled. And in fact, having a low pressure drop system will have impact on your heights. And so having that conversation early on with the engineer really helps, because then they know the intention is, because ductwork, you know, is like Sarah mentioned, like an afterthought, like, let's just somehow hide this stuff. So I think, having that intention can have huge savings on fan energy, and saying that upfront as one of the goals of the project really helps. Otherwise, it's not business as usual in many cases.
Yeah, and then you get to the end of the design and you're looking at your modeling results and you're like, whoa, that's a lot of fan energy.
Yeah.
Like, oh, then you can't do anything about it.
Awesome. I think we hit all of Brian's questions, so I'm going to switch over to one of David's questions, which is specific to one of Ramya's examples, where space cooling didn't show a large reduction over the year, but it did have a large reduction in peak cooling load, which would impact sizing of systems and thus improve the first cost. Can you speak to the types of key takeaways that could be unpacked with a client and architect from that modeling?
Sorry, which slide is that?
I can go up.
It was an earlier slide, but it's more of a general question of, in that particular one, just seeing there was a reduction in the peak load. Nope, go back. It was the chart with just the text. There you go. So in this one, you look at the, I think it was this one.
So this one is your system peak load. Is that what you were looking at, or are you looking at the number 22 slide?
I can't see the numbers here. Was this the one?
Earlier than this, like I think very beginning, probably the 4th slide. Next one. Next. Yeah, this one.
There we go. That's the one. So you see here in your space cooling that the baseline for the whole year only goes down by 18%. But when you look at your peak for baseline versus the building, it's almost half for the proposed building. So this is a question about sort of, when you look at this information, you may see something that doesn't initially, in totality, indicate that you're getting a benefit from it, but there probably actually is a benefit that needs to be, you know, sort of unpacked with the client. And this is just one example. So it's sort of like pulling back, like what are some of the key things we should be looking for, and not just get so focused on like the total EUI piece of this.
Absolutely. And a lot of this, again, because the baseline system in this particular case was a packaged heat pump, you know, whereas the proposed is a DOAS unit with BRF system. So there are a lot of controls that could have tilted the energy use itself. Like, for example, we are doing better dehumidification than is happening in the proposed, in the baseline. So I think you're bang on when you say that looking at that peak is very important, and not just looking at the energy consumption and saying, well, you know, you've just designed a VRF system and, you know, it's still not saving energy. So I think the idea is to look at the inputs and verify them to confirm that the model is indeed working as we've designed it, and that we're heading in the right direction in terms of like reducing peak load and optimizing our systems, not just from an efficiency standpoint, but also like, you know, actual loads in the building and envelope and people and lighting.
I think that's a really astute observation too, because it gets back to one of the previous questions about like the life cycle cost analysis, right? And if we're really, you know, trying to do better integrated and integrative design, then it's about all of those things. It's not just the EUI, it's not just the operational carbon, but it's also, you know, the first cost dollar savings of peak, you know, whatever equipment sizing, and that gets into like it depends if it's a air handling unit with a cooling coil versus a packaged rooftop, what the savings are going to be. But then, you know, we want to look at things like if there's, you know, electrochromic glazing, you might save the cost of internal roller shades, and that affects your HVAC systems too. So all these things are really related. And I think it's very, mindful to be thinking big picture in that context.
Great point, actually, David.
Well, I remember hearing from Payette giving an example of one of their Coat Top 10 projects where they did triple pane glazing. By doing that, they eliminated every bit of perimeter heating to the envelope. And this was in, the middle of Massachusetts. And it was one of those things that came up as a VE with the client from the contractor that they could save, I don't know, $800,000 if they just go to double pane glazing. But because it was integrated and because they went back to their engineer, they could say, well, now you got to upsize this, and it's going to have a 1 million plus price tag because we have to add this component and we got to upsize our system. So it's just sort of understanding that relationship of how you're going to optimize the building and what that might allow you to reduce in size or eliminate because of how you've thought this through from a performance perspective.
Yeah, and that example, David, is a classic example. And that is one of the only ways, or one of the few ways, we can justify the triple glazing in cool climates. I think that's a classic example. Yeah.
I think, in our experience, having that exact same conversation too, it having kind of an informed contractor or price estimator or whoever's doing the budgeting on those numbers when you get to the VE process, to be able to get the appropriate credits for those things is sometimes challenging. So I think the understanding that these things are related, definitely, like, we need to make those connections early on too, so that it's, you can value them appropriately when you get to that point.
I would just add, I think that's a great example of why architects need to understand this process and understand what those decisions have been made, what decisions have been made along the way. And maybe as just, I know we're getting towards the end of our time here, but in terms of the process of working with architects, and maybe I'm jumping into one of the preset questions a little bit here, Janki, but, do you have recommendations on kind of when certain decisions need to be made? And that, I know that's a big question, but you talked about when you can kind of go and optimize your model. It's kind of after you've made a lot of these comparative analyses. And I'm just, maybe if you could just speak for a moment on kind of how that architect engineer interaction around the energy model, kind of is most productive in your experience.
I can start off. I think the most productive time to investigate or to make those decisions is SD or even pre-SD. It's always good to have, there are two types of, there are many types of projects, but some of the types of projects that are very successful are the ones that actually have goals right at the beginning. So there is like a shoebox model that's run, and there are some goals that are set, and even discussion on what parameters and what parameters should be that we should have goals for. I think those projects end up in a better place than the ones that just, we want to be 20% better than coal, or we want to be like 30% better than coal, or we want to be gold. So rather than having that, going into specific details, like we want to hit 30% window to wall ratio. We want to have, daylight autonomy for X amount of spaces, or, this is our glare goal, or, so having very detailed goals really helps compared to just having like an overarching goal. And therefore, when you have those detailed goals, you ensure that your analysis is able to, constantly provide feedback on those goals. So I think SD is a good time to do that. But SD is also a good time to do pricing, because what I've observed is that you make all the right decisions, you do all the right analysis, and then comes end of DD, and then you go back and do a whole bunch of things that you already did. So you have very ambitious goals in SD, and then you carry that forward, and then come BD, the project is over budget, and then we like almost 50% of whatever you decided in the SD stage. So I would say SD for pricing and for having smaller goals, not just a big overarching goal.
Yeah, I think the real magic happens if you're able to get that early pricing and then add it into your analysis with, like if a roof insulation R30, R40, R50, whatever, and then like dollar per square foot or however the pricing is set up, and then build that into your parametric analysis and your parallel coordinates. Because ideally, we're going to optimize first the things that you don't have to actively maintain. Like we kind of talked about ongoing operations and set points changing and people kind of messing up design intent. But if it's something like a triple pane window or more, continuous insulation in the walls or better air sealing and air barriers, continuity, those things you can't really go and mess up as easily. So it's kind of like first optimizing the things, frankly, like that are envelope driven, and then kind of like the stuff and the systems like lighting and HVAC and plumbing and those things.
Awesome. Paul just made a really great comment in the chat box about using the OPR to set some of those goals earlier on so that you have them as a something to guide you along the process, something to look back to. I thought that's a good tidbit to share with the rest of the audience. It wasn't really
if you can get that fan static pressure in the OPR, that's
the other thing that is successful is having the client vote low, medium, high in terms of what they value in terms, whatever sustainability goals that we have. So having them vote on it, because what happens is when the VE process does take place, you have that as your sort of guiding light, even if people want to ignore it, but at least it is there, it is documented that this was important to us at some point. So I think that is also another thing that has been successful.
Yeah, then you can remind people back, like, remember when you said this was important? Like, is it still? Still important?
Yeah.
Yeah, totally. That's what I mean. The OPR, that's what we need to rely on.
Yeah, I feel foolish for not like putting that front and center as the first thing we talk about in this session.
It was like implied. Yeah.
But yeah, so we are almost out of time. We have 2 minutes left, and I wanted to use that time to just point out the next 2 sessions that are coming up. I know Josh mentioned it, but just a little more detail. So next month, we're going to be partnering with IBIPSA, actually. So we have a couple of speakers from the, don't ask me to tell you what that acronym stands for, but it's the International Building Performance Simulation Association, maybe. I probably got that wrong, but they are right. Going. Oh, yay. Okay. So we're going to have a couple of people in their BIM to BPS group join us to talk about tips and tricks and common errors when you're modeling in Revit or another BIM software program, and translating that model to an analytical energy model that people like Sarah or Ramya would take and run an energy model on instead of rebuilding the whole model from scratch.
Which we would appreciate.
Yes, that. And we're going to have Mustafa or Chris, I'm not sure who, from Ladybug's Tools join us to talk about their new tool Pollination, which has some new workflows that allow for some more seamless translation, and they're going to talk about that. So I really hope you'll be able to join us then. And then in December, we're going to be talking about contracts. We're going to get the architectural perspective, the engineering perspective, and we're also trying to line up someone who can talk about starting an energy model as an architect and then transitioning that or using that to input for inputs for a like a full building energy model that an engineer would do. So we'll have 3 different workflows and contract language or information around that in December. So that will be the end of our year on breaking down barriers to building science. And if you're looking to join, I just realized we forgot to update the date, is the 3rd Thursday of each month. So the 21st, October 21st will be our next meeting. It's from 8 a.m. to 9 a.m. in the morning. And we'd love to see you join us in our monthly meeting. Thank you, everyone. Thank you to our presenters. It was an amazing session. Lots of great questions. All right.
Yeah, thanks for having me. Thanks everybody for your questions. They're great.
Thank you, everyone. Yeah.
Thanks so much for joining
Have
us.
a good night.
Thank you all.
Thank you.